alguno de ustedes que trabaja en celdas combustibles, pues esto es un tema de gran interés. Pero también hay otra serie de aplicaciones que son en donde el tema de líquidos iónicos a temperatura ambiente es de mucho interés, de verdad. Con ustedes entonces al profesor David Price.
Well, it's a great pleasure to be in Cali, and I'd like to thank Walter and Maria Elena for arranging the invitation. It's been a very interesting 3 days, and I must say I've been very impressed. Everyone I met has been so excited by what they're doing, and that's really a great thing. So today I'm going to talk to you about a class of materials called room temperature ionic liquids. Ionic liquids is kind of a new name for what in the past I suppose experimentalists called molten salts and theorists called Coulomb liquids. But now they're generally called ionic liquids, and this is a special class. Of course, most molten salts or ionic liquids melt at well, several hundred degrees centigrade. But there's a certain class I'll talk about which actually remain liquid down to room temperature or even below, and this leads to lots of very exciting potential applications. So a little bit of the history. Actually, they were first synthesized actually in 1888, so quite a long history. And then along the way, kind of many important advances. And for example, especially in the 1980s, the first publications in which they were kind of touted as being important for reaction media, catalysts and synthesis and so on. Just to give you some idea of kind of the level of work on these systems, this goes up to 2006, and you see a dramatic increase in the number of papers due to both interest in the science and lots of important applications. And of course, you can imagine this is up to 2006, but you can imagine it's really taking up through the roof if we count everything going on since then. So you could ask, you know, with all this work that's been done and going on, you know, what can one person contribute to all of this? So I guess in my case and my collaborators, we are mostly specialists in scattering techniques, neutron and X-ray scattering, and I'll show you a little bit about these. So we've kind of thought maybe that there haven't been many papers on this dealing with scattering techniques. So we kind of asked the question, what can we as neutron scatterers or X-ray scatterers contribute to our understanding of these systems? And then why the interest represented by these publications, and then some of them are listed here. Very important one, green chemical processing, that you can get rid of all these horrible organic compounds, traditional solvents which do harm to people and to the environment, and instead use these rather benign systems. And in addition to replacing the old solvents, they have the potential for changing the way they're employed, and also kind of other applications, engineering fluids, new materials in all these industries. And what's happening a lot recently is the idea of using these systems either by themselves or in kind of conjunction with other materials as electrolytes in advanced batteries. So that's a little bit on the technology. So now describe a little bit what we have been doing, myself and my collaborators. And we have kind of chosen a particular system based on, which is almost a classical cation in these systems. This is the imidazolium cation, this kind of ring here. There's an alkyl chain going off at one end, and it's actually this large and very asymmetric cation which prevents them from freezing as you cool down. So this special class of ionic liquids, it's these this large and asymmetric cations which prevent them from freezing until you get down to room temperature or even below. And then you can add various anions to this. It doesn't matter. The anion is sort of in a way less important. So in these experiments, we just chose a simple monotonic anion, actually bromine, for reasons to do with the X-ray experiments. So I'm going to talk about two kinds of techniques. I'll describe them a little bit in case some of you are not familiar with them. Sorry. Okay, then you can hear me better. Yeah. Okay. So this is the first thing I'm going to talk about is what we want to measure in terms of structure, and there we use, of course, as all of you know, I'm sure, diffraction techniques, and you can use either X-rays or neutrons. And well, I think all of you are familiar with it, but just to kind of establish in a way the notation, then a diffraction experiment, of course, you take a beam of well, whatever particle you want to use, neutrons or X-rays or electrons, send it onto your sample. You measure the scattered beam by putting an appropriate detector here, and essentially you measure the intensity in this detector. And as you probably know, a scattering intensity is usually described in terms of a cross-section. That's the probability. Sorry. The probability for a particular instant particle to be scattered into an element of solid angle d omega. So you measure something called d sigma by d omega, a cross-section, and then you take out some sort of unimportant terms, the number of atoms in the sample, the form factor, which describes the strength of the interaction of the whatever particle you're using with the sample. In the case of X-rays, it's a form factor, and in the case of neutrons, it's just a scalar quantity, a scattering length b. You divide all these things out, and you get a quantity which we call the structure factor S of Q. So that's actually a dimensionless quantity, and it's a function of what we call the scattering vector Q, which is very simply just the vector difference between the incoming and outgoing particles. For elastic scattering, which is generally the case with X-rays and most often with neutrons, you assume there's no energy transfer, so the incident and scattered wave vectors have the same magnitude, and they're just which is 2 pi divided by the wavelength of what you're using. And in this case, the magnitude of Q is just given by 4 pi sine theta over lambda, where 2 theta is the scattering angle. So those of you who do X-ray measurements in the lab, you're probably used to plotting things as a function of theta or 2 theta. In these sort of experiments on liquids and glasses and other disordered systems, it's more common to talk about this this scattering vector Q or its magnitude. So we measure the structure factor S of Q, And it has a very simple interpretation. If you have a system where every atom, a given atom I is at a position R at a particular time, we can call it time 0. Then it's just the sum of all the phase factors between pairs of atoms, averaged and divided by the number of atoms. So essentially, diffraction technique is giving you like a snapshot, an instant photograph of what the system is looking at one moment in time, of course, averaged over many different moments in time, or if you like, averaged over the ensemble, which comes to the same thing. Okay, so this is a particular instrument which we used in our experiments. This one happens to be located in Japan, and it gives you a scale. You see then the more powerful X-ray diffraction instruments are based at synchrotron sources. As you probably know, there's synchrotron sources many places in the world. I think the biggest, nearest one to here is probably at Campinas in Brazil. So here we have one of the many beam lines coming off the synchrotron. X-rays are coming through this device, various slits to focus them. A sample inside this shielded device here. It might be controlling temperature or pressure or whatever. And then here's a detector, in this case a germanium solid state detector, measuring now the intensity of the X-ray scattering in this detector. And this is essentially the sample. This is a typical size of sample. We show here kind of reference to a coin. I think this is a Japanese 10 yen piece or something like that. And then this is a typically size of sample, normally contained within a glass capillary. And in doing that, so then what we did is we looked at 3 of these liquids I showed with different lengths of the alkyl chain at the end. And these are often called then by the name of depending on the number of carbon atoms in this chain, we call them ethyl, methylimidazolium bromide, butyl, or hexyl. Or if you like, sometimes you see this is called C2, C4, and C6, which is the number of carbon atoms on the alkyl chain. So one thing we are interested in with how does the structure of these things differ when you make the alkyl chain longer and longer. So here's then the structure factor which we're measuring at this instrument in Japan. And if you have a liquid or a glass, unlike in a crystal where you have Bragg peaks or sharp peaks coming up, a liquid or a glass, you have a diffraction pattern which is continuous, but it still has quite a lot of information. And in particular, you're interested then in some particular features, and for example, the peaks which appear in this X-ray, in this scattering spectrum, as you increase the scattering vector Q, which I described earlier. And one thing which stands out immediately, as if you make the alkyl chain a little bit longer, you start with 2 carbon atoms in the chain, put 2 more carbon atoms to make 4, 2 more to make 6. You have this peak at very small wave vector Q coming up dramatically as you increase the length of the alkyl chains, whereas the other ones, which are due to the sort of overall structure of a liquid, isn't changing too much. So an obvious interesting feature, question to ask is, what is giving rise to this feature here, and why is it increasing as you make the alkyl chain longer and longer? Well, one way of getting a picture on this, and now it's almost routine to do, if you're doing a kind of serious scattering experiment, to do computer simulation in conjunction with it, because as you see, the problem is a scattering experiment really only measures things as a function of one variable. That is, if you have a system like with a liquid or glass, there's no preferred direction, so you just get information in one direction. If you have a computer model, you have, say, a box with 1,000 atoms in it, and you then do a numerical simulation how these atoms move around, then you have kind of three-dimensional information. And so what you're often doing here is kind of using, in a way, the scattering experiment to kind of validate the computer simulation. And then, obviously, then the first thing to ask is, well, how well is the computer simulation given by blue? Blue is for molecular dynamics. Compared with the red curve, which is the X-ray diffraction data. And as you see, the agreement is actually very, very good. And what's remarkable is in this particular simulation done by our collaborators, this first peak here is even that is well produced, which is not always easy to do, because a feature at small q or small 2 theta, a small scattering angle, corresponds to a very large distance. So you have to have a large box in your simulation to interpret these features correctly. So what is our conclusion with this? As I said, the structure factors from the molecular dynamics are in good agreement with the experiment. And in particular, this low Q peak is well produced in these 2 liquids where it appears. And now, if you're talking about the actual quantities, you can relate the position of this peak in Q, which is a fraction of an inverse angstrom. If you take 2 pi divided by Q, you get a distance, and with these peaks, you get distances about 14 and 18 angstroms, 14 in the case of what I'm calling B-min bromide, and 18 in the case of H-min bromide. So there's something in this material where you're having these quite long structural calculations. Normally, atomic atoms are nearest distance between atoms is 2 or 3 angstroms. And in this case, we're getting correlations in the system which are much larger than that, an order of, maybe almost an order of magnitude larger. So then you ask, why is this? And there have been various explanations for this in the literature. And one which has received a lot of attention is the idea that you have some kind of micelle structure in the thing, that you have the tail, the ends of these alkyl chains kind of coming together in the middle, and then the head groups, the imidazolium rings kind of on the outside, and the cations next to them. So this imagines then that you have some kind of micelle type structure. Actually, so what we have found is we don't find any evidence of this, but of course there is considerable evidence for nanoscopic heterogeneity. Heterogeneity means that the system is not uniform. There are places where it has one kind of structure and other places where it has another kind of structure. And the scale of this is on the order of 10 to 20 angstroms, which, as you know, corresponds to 1 to 2 nanometers. So we call it nanoscopic heterogeneity. And so why does this, what is the reason for this? And what we think is that it's somehow, you can look at kind of crystalline analogs of these systems. The interest, of course, is that they don't crystallize at room temperature, but still you can go down to low temperature and crystallize them and look at the structure. And if you look at, this is a computer simulation now of the crystal, and if you look at the structure, rather than the tail groups kind of coinciding, coalescing in a point, they seem to sort of coalesce in layers. So you have a kind of layered structure and then these you have then these planes of these head groups coupled with the bromine anions. And it turns out that in the crystal, these distances between this plane and this plane are on the order of 15 angstroms. And then it's then the scattering, it's a bit like Bragg reflection. Then the scattering, interference between the scattering from these planes, it's what giving rise to, in the solid, very strong Bragg peaks. And when you melt it, what we see with these low Q peaks is kind of a remnant of these kind of interplane correlations in the liquid. Okay, so that's a little bit now on the pure ionic liquids. Now, in actual fact, these things are often very hygroscopic, and in practical applications, almost certainly they're going to be exposed to water vapor, number one. And number two, if you're using them with solvents, as solvents, you're going to be mixing things with them. So then the question is, how do these things compare when you dissolve it in some solvent or another? And so we went on to look at the question is, what happens to these room temperature ionic liquids when you add water to them? And of course, there is a lot of information about this. It's an important question for the reasons I said. And there are fairly dramatic effects. And these are some data in the literature. This is, for example, density. This is plotted as a function, concentration of the ionic liquid. So at the right hand axis, this is the pure liquid. At the left end is pure water, and you see this kind of gradual decline when you go to the density of the liquid and the density of water. Maybe that's not too surprising, but then if you look at conductivity, this is a little bit more dramatic. Here's the conductivity of the ionic liquid. I don't know, something of the order of 5 millisieverts per centimeter. And then you add the water. Again, perhaps not surprising, the conductivity increases. But perhaps more surprising is it actually gets to a peak. And then when you go to pure water, it increases again. So there's somewhere in the middle when you have then conductivities much higher than either the pure water or the pure ionic liquid. And so what is the question then is, what is giving rise to this? And can we look at the microscopics of the problem to see why this might be? And actually our collaborator, Oleg Borodin at the Army Research Lab in the US, has done some simulations and actually able to get really rather amazing agreement to density, conductivity, and other things like viscosity, which I don't show here. So then we've been doing scattering experiments, going from the pure liquid, and then in this case, it's a C4. This is before what I call the BMIM, the cation, the butyl imidazolium. Here we have actually not the for various reasons, the molecular dynamic. People were more interested in the BF4 anion than the simple one we chose before. Anyway, the important thing is that when you then add water, in this case, you get rather significant changes in the structure. And what seems to happen here is that this low Q peak, which is like we found in the bromide, kind of already appearing, seems to be suppressed when you add water. And whereas when we go to another system, when we now increase the alkyl chain to have 8 carbon atoms, and this is called octyl, methyl imidazolium, octyl, because there are 8 carbon atoms on the chain. And here, remarkably, and we don't quite understand why this is, we seem now to have very little difference in the structure when we go to pure water, and then the purple curves are like a 50-50 mixture, one molecule of water for every anion or every cation. Somehow in this system we don't get very much don't seem to get very much changes in the overall structure. And so what is happening here? Well, in the pure liquid, as I said, we have this nanoscale heterogeneity. And when we add the water, this seems to be being replaced by a kind of clustering or segregation of the water molecules in such a way that almost by coincidence, the overall scattering function is not changed very much. So as I said, Borodin and collaborators have been doing calculations of this, and when they look at the energetics of the problem, what they seem to find is that there's a positive excess enthalpy, which indicates a preference for ions to interact with each other compared with water, consistent with the water clustering. And now I mentioned what's very nice about computer simulation is that you have this box chosen to accommodate a kind of a fairly large number of molecules, water molecules. What we're showing here, it's a bit hard to sort out, but the oxygens of the water are shown in red, and the anion, as I said, is BF4, boron tetrafluoride, and we've put the fluorine atoms of the anion in green, and these, whereas the alkyl chains, the things coming up the end, are the sort of black sticks. And then you can kind of just looking at it, you have a segregation. You have regions where there are a clustering of the water molecules and the anions, and then regions where you don't have any of those, but you just have the alkyl tails. So what this seems to be saying is that when we're adding water in this particular salt, the C8MnBF4, we're not really changing very much the degree of the ion correlations very much, whereas so while you're changing the viscosity, somehow the ionicity in the system is not changing, changing very much. And then the other thing you can do, of course, with a computer simulation, you can get nice sort of three-dimensional correlations. You can see how the various atoms, let's say, of the water molecules, which are shown in red here. This is kind of a contour plot of the oxygen atoms of the water molecules, and so the red is showing where the contour is above a certain level, and here is the same thing in yellow for the fluorine atoms and the BF4. So what we're finding then, that in both these cases, you're having kind of a clustering around the hydrogen atoms on the imidazolium ring. But then here, what you're finding for the oxygen of the water molecules, that they're also kind of sticking around the nitrogen atoms, shown in blue here, the nitrogen atoms in the imidazolium ring. So you can get lots of, if the point is, if you believe the computer simulation and the good agreement between the simulation and the scattering experiments gives you confidence enough to do so, then you can get this very, very detailed information, in this case, structural information from the simulation, and then getting structural insight, and then also using the simulation to calculate the macroscopic properties I mentioned, like density and viscosity and conductivity and so on. Okay, so this is on structure. Just to summarize, then three various kinds of order associated with the peaks in the structure factor, the nanometer scale heterogeneity with the longer alkyl chains, and this, which is kind of on the whole preserved with the addition of water, probably reflecting this clustering of the water atoms, of the water molecules, and the and the anions. Okay.
Y los aniones, entonces ahora creo que por eso
I've talked so far about structure, but neutron scattering is also a very important technique for looking at dynamics. And neutron scattering is one of the techniques, if you like, spectroscopic techniques, which give you information both in time and in space. Right? Often optical spectroscopy essentially just gives you kind of information as a function of, finally get used to this, as a function of time. But what you also would like to do is at the same time get information about time or frequency. At the same time get information about what's happening in space. That is, if you have a particular excitation at a certain frequency, well, what are kind of like the motions in space that these correspond to? So there are various techniques which do this, and in particular neutron techniques, which are shown by this yellow curve, then actually able to span quite a large region of this sort of distance time scale range. This is plotted in angstroms, so you can go to kind of fractions of an angstrom to perhaps 100 or 1,000 angstroms, so you're getting to, let's say, 100 nanometers, and then on the time scale you can go from kind of fractions of this is shown in picoseconds, so this would be 1 picosecond, 10 to the minus 12. So you go up here to nanoseconds and then down here to microseconds. So neutron scattering as a technique then covers quite a big range of the length scales and time scales, which are interested in condensed systems. How do you do these experiments? Well, they're very, in a way, a sort of slight variation on what I already showed you in diffraction. You do a scattering experiment like you did before, but the difference now is you measure in addition to measuring the intensity in this detector, you can measure at the same time measure the energy change. That is, the neutron that's arriving in this detector, have they speeded up or slowed down as a result of the interaction with the sample? And this you were described in a rather similar way in terms of a cross-section, but now your cross-section depends on both the scattering vector Q and the energy E. So in terms of, if you think about Fourier transformations, the Q dependence gives you information in space, and the E dependence gives you information about in time. And if you want to look at the mathematics of it, what you're looking at here are really correlations. Before, with diffraction, we looked at one atom at time 0 and the other atom at another atom at time 0. Here we have kind of one atom at time t and the other atom at time 0. So it's as if you're asking, how does the structure which you measure in a diffraction experiment, how does it develop in time? That is, if you're not just taking a snapshot of one moment in time, like you have like a movie of how it's developing in time, something like this. So there's lots of kind of subtle information in these things. And why are we interested in dynamics? Well, the design of specific liquids may depend on the dynamics in different environments. And as we've seen, small amounts of water can have significant effects. And for example, viscosity and conductivity, these are obviously important and may significantly change reaction rates in practical applications. There's a very nice, if you're interested, a very nice review of this by Fire in Stanford. Okay, so I'll say a little bit now about less detail, I think, about the inelastic scattering experiments. This is a little bit the same. This is an example of two experiments. They're very similar, one in Berlin, Germany, one in Grenoble in France. You have your neutron beam here. It's kind of collimated to come in its own direction. You hit the sample, you measure the intensity into these various detectors arranged at different angles. And but the other thing you do here is you have a number of choppers in the beam. You have one chopper fairly near the source, another chopper right in front of the sample, and these kind of determine the time at which the neutrons either left the source or arrived at the sample. And then because the energy of a neutron depends on its velocity, these phase choppers then essentially enable you to determine the velocity and hence the wave vector of the neutrons before and after the scattering event. So what can we learn about these same systems with scattering experiments? One thing you do is you just look at the kind of elastic scattering. This is scattering which you'd get if the thing was completely solid. So you start out at room temperature, you have intensity normalized to 1, you heat it up, and then this intensity goes down. And what this shows you are the various kind of relaxation processes which are setting in as you heat the sample up. And finally, when you get to the melting point, basically all the elastic scattering disappears. By definition, a liquid has no elastic scattering. And so from the fact that you can identify maybe 3 slopes in this behavior before you get final meeting, this gives you a clue that there's maybe at least 3 kind of complex processes going on in this system. In other words, 3 kinds of relaxation. So then it's a challenge, if you look at the detailed scattering, to figure out what is going on. And then typically then what you do is, I mentioned you're measuring something as a function of a scattering vector Q and an energy E. Usually what you do is you fix the value of Q and look at the scattering as a function of energy. This is the elastic region where there's no energy transfer. Here the neutrons gain energy, here the neutrons lose energy. And from the details of this of these spectra, they're often called quasi-elastic. I said a liquid has no elastic scattering, but it has scattering centered at the elastic region, which look a little bit like it. From the shape of these curves, and especially the way that they broaden as you heat them up, then you can get detailed information about the various relaxation processes. And in the pure liquid, what we do is actually, in these experiments, identified one process, one we call a fast process, which we can associate with kind of translational diffusion in the solid. And this translational diffusion you don't get until the thing melts. Obviously, there's very little diffusion in the solid. Whereas in a faster term, you have some relaxations. These are the ones that start to come in when you just start to heat the solid. You already have some of this relaxation in the solid, but then it increases dramatically again when you go through the melting point. And from the details of these curves, then you can get quite kind of detailed insight into what's going on in these different relaxation processes. So there's lots of detailed information here I don't have time to go into. So then the question now is going back to what happens to you when you add water to these systems. So we were making we've been making measurements. In this case, again, we went back to Japan. We went to a neutron, one of the newest neutron sources in the world, which is called JPARC in Japan, and then measured the what we get in these systems. As I've shown, you fix a certain value of Q and see what happens to the broadening as you heat the thing up. And again, you can then identify two processes, and in this case, we're looking at the diffusion process. And here we're starting out with the pure salt. We then add liquid till we get up to the 50-50 concentration, and you see then you have a width of these curves increasing as you go up in water concentration, and so you have a large increase in the diffusion on adding water with, and then we're also interested in isotope effects. What happens when you replace H2O with D2O, and we find some subtle differences which kind of taking us beyond, let's say, classical chemistry into quantum chemistry. So we can get all these information from the scattering experiments, and now again, how well do the computer simulations agree with this? So what we're plotting here is essentially what is happening when we increase time. So we're looking at some intensity here at time 0. This would correspond to the diffraction experiment, and how this system is relaxing as we increase time down to times of 1 nanosecond or 10 nanoseconds and longer. So here we have the pure salt. What we've able in the neutron scattering experiments, we actually can pick out 3 different motions corresponding to different kinds of relaxation rate. The red one is actually the diffusive process I talked about before, just the pure translational diffusion, and then these are various, the green, the purple, and the blue are then some local relaxations. And when you put all these together, you get kind of like a total relaxation of the system, which is corresponding to the solid black curve. And then from the molecular dynamics, these are the squares. You get actually a remarkable agreement between the computer simulation and the neutron scattering experiments. When we add water, then everything speeds up. Here you have to go down to 10 nanoseconds until basically the relaxations disappear. Here, they already almost disappeared by 1 nanosecond. So, as we said, things are everything is kind of speeded up when you add water to the system, and this is, of course, consistent with what we saw happen with the conductivity, for example, conductivity increasing as you add water to the pure system. Okay, so what you can do then, what I showed before, is the diffusion of the imidazolium cations. With some difficulty, you can also extract from these experiments the diffusion of the pure water, and again, you're getting quite good agreement between the neutron scattering, which is the solid black curve, and the molecular dynamics. Now looking at just at the dynamics of the water molecules. So both for the cations and the water molecules, again, actually amazingly good agreement between the computer simulations and the molecular dynamics, and therefore we can use now the molecular dynamics to extract detailed information, both about the dynamics of the water and the cation and the anion, and beyond that, the different components of the cation. For example, the head group, the imidazolium ring, compared with the alkyl chain. And
con
then
la
just to
cadena
summarize
álquida. Entonces,
from the
solamente para
dynamics,
resumir,
we've
lo
seen
que
the
podemos
complex
aprender de
scenario,
dinámicos,
dynamical range extending from
tenemos
picoseconds to
un escenario
nanoseconds.
complejo. Mi punto
I
que
haven't
se
had
extiende
time. We
de
can get detailed
nanosegundos
information
a
about ethyl
picosegundos. No
group
sé si tengo
rotations. I haven't had
tiempo, no
time to
tuve
go
tiempo
into
para
that.
hablar de las rotaciones del
We
grupo
found that
EPI.
addition of the water is speeding up
Nos
the
dimos cuenta
dynamics of the
que
ionic
cuando
liquid
agregamos agua nos
due to
acelera
faster
la
diffusive
dinámica del líquido
modes,
iónico debido a los
whereas
modos
and the
difusivos
water
que son más rápidos.
dynamics, while in the
La
mixed
dinámica
system,
del
the
agua,
water, as we've seen, is
como
moving
vimos
much
en un
faster
sistema más grande, el
than
agua se
this
está moviendo más
this
rápido.
large imidazolium cation.
El catión
Still, it's
grande
much
en el
slower than in
sodio,
pure
sin
water.
embargo, sigue siendo
So adding water
mucho
to the ionic
más
liquid,
lento que en el agua pura.
if you
Entonces,
like,
cuando
it's speeding
agregamos
up the
este
dynamics
líquido iónico está
of the ionic
acelerando
liquid, but you're adding
la
ionic liquid to
dinámica
water,
del
you're
líquido
slowing
iónico, pero
down the
cuando estamos
dynamics of the
agregando el
water.
líquido iónico
And
al agua, estamos
so we
disminuyendo
are
la
doing
velocidad
lots of work
de
in
la dinámica.
progress to
Entonces, eso sería un
identify
trabajo para
the different
identificar
motions
estos
involved. So this
diferentes
is kind of like the
movimientos
status
que están
report,
involucrados.
if you
Esto
like,
sería
on
como
where we are
el
now.
reporte del
So I'd
estado en
like
el
to
que estamos
end
en este momento.
by
Entonces,
listing my
quiero
collaborators.
terminar
Actually,
aquí
most important
dándole un
collaborator
listado de mis
is Marie-Louise
colaboradores. Mi
Sabunji, who
colaboradora
is
más
some reason left out
importante
of
que
this
por algún
slide, but
motivo no
she's
está
my most
aquí
important
lista. Ella es mi
collaborator in
colaboradora
this
más
and in many
importante
other
en
things.
este y en muchas
And
otras
these are various
cosas.
collaborators
Y esos son
associated
otros
with the
colaboradores
molecular
que
dynamics,
están
the X-ray
relacionados con la
experiments,
dinámica
the
molecular,
Newton
los
experiments,
experimentos de rayos
and
X
the
y
group at
de
University of
neutrones, y el
Tokyo who've
grupo de la
been
Universidad
important
de Tokio, que ha sido
in
bastante
making
importante
in
para mí
making the
para
samples.
lograr
And
obtener
so
las
I'd like to thank
muestras.
you for your attention,
Muchas
and
gracias por su
I should
atención
also like to
y
thank our excellent translator here.
darle
I
las
think we
gracias
knew
al
that,
traductor
and his brother.
y a su hermano también.
We've already known that science crosses national boundaries.
Que
I
nos
think
permite
what
darnos
we've
cuenta
seen
que la
here is
ciencia
that
cruza
science
barreras.
also crosses
También
language
nos damos cuenta que
barriers
la
without
ciencia
too
también
much
cruza barreras
difficulty.
del lenguaje sin
And
mucha dificultad.
also the young people who've been involved in the audiovisual and the internet, the simultaneous internet recording. And so thank you very much.
Muchas gracias.
It's okay.
Ok, bien. Entonces, antes de empezar con la sesión de preguntas, quiero sinceramente agradecer a todas las entidades que han hecho posible estas presentaciones. Por un lado, diferentes oficinas de la Universidad del Valle, en particular el programa de posgrado de física y el programa de posgrados de química. También al Consejo Profesional de Química de Colombia, quien nos ayudó bastante con pasajes internacionales. Queremos agradecer también a ICETEX. Agradecemos también a la Academia de Ciencias Exactas y Naturales de Colombia. Esta serie de eventos hace parte, digamos, de tres eventos grandes en general. En primer lugar, estas presentaciones hacen parte de la contribución de la facultad y de los departamentos asociados a la Facultad de Ciencias Naturales a la celebración de los 70 años de la universidad, por un lado. Pero por otro lado también al evento de Ciencia, Mujer y Tecnología que ocurre en varias universidades del país y se celebra a lo largo del año. Y finalmente, estas presentaciones, digamos, los profesores de aquí luego van a las otras universidades en Colombia, a la Universidad Nacional, a la Universidad de Antioquia en Medellín, y esto es porque queremos, digamos, fortalecer un programa de cooperación entre nuestras universidades para compartir visitantes internacionales de muy alto prestigio. Y ahora sí, entonces, ¿preguntas? Profesor Rubén Vargas.
I would like to know if by adding water to your liquids, to your ionic liquids, there's a threshold, and how this is affected in the conductivity. There's a critical point, a critical concentration in which there is a critical point, a critical concentration of water.
Oh, yes. Well, actually, we see there's this is a very important issue. Is the question is, are you really dealing with a pure solution, or are you dealing with a are you having phase separation? And actually, what we try to do is keep away from make sure we're in a region of the phase diagram where there is where there is a complete solution. And in fact, what we found is that in this particular case, as we got kind of towards the where we kind of just adding a little bit of water to the salt, we're finding this upturn here, and this upturn is kind of a suggestion of a small angle scattering, and for small angle scattering is a sign of phase separation. So we see something like this, and this is a warning that we we're getting too dangerously close to a segregated system. Was that your question?
Yes, and how is related to the conductivity behavior?
Well, I would say that's in progress, and when we're working with our molecular dynamics colleagues to look at that. Yeah.
Okay, thank you.
Yeah.
¿Qué comportamiento tendría esas sales que estudiaron específicamente en un alimento? Si tuvieron el comportamiento en un alimento.
Some kind of food product. Well, I don't know. As far as I know, there are as far as I know, there are no plans to add these systems to food. Perhaps a slightly related issue is what is happening? What will happen when you confine them? Like there are, for example, if you're going to use these things in battery as battery electrodes, they're going to have to kind of intercalate into the anode and the cathode. So important question is how are they going to behave when you put them in a small pore or restricted channel? That is kind of a new direction where we want to pursue this work. Yeah.
What about the dimension of those?
Of those? Well, they can be nanometers. Yeah. So that.
No, maybe of the separator as electrolyte. As a membrane or something like this.
Well, there'll be membranes and there'll be electrodes, but there's going to be a lot of these. The things are made kind of porous, right, to let the electrode come in good contact with the electrolyte to come in good contact with the electrode. So you can have micro, there can be sort of micro or even nanoporous behavior in them. This is an important question.
That is a technical question. It's about how is the computer time to do these calculations?
Yeah, they can be essentially what you do, especially of course, computer simulations obviously take longer when you have more atoms, or your box is getting bigger, or when you're looking at longer and longer times. And actually, in these systems, you want to have a big box with lots of atoms because you have these very long-range correlations, and also you have these a big range in time for the diffusion processes. So you want to run at long times as well. So essentially, they can be hours or days. So what you do essentially is make your box as big as you can, and make them to be consistent with the available computer time. But of course, one thing here is what I'm showing here are classical molecular dynamics. So if you look at the quantum mechanics and do ab initio computer simulations, that would take much longer. In fact, you probably couldn't do them at all on a system as complicated as this.
For the X-ray measurements and the neutron measurements, how long is the time to do the spectroscopy or the
yes. Well, of course, actually, if all the experiments I've shown are done at big facilities, and you have to write a proposal, and there's a committee which views them. So time is very limited. Typically, for the neutron experiment, we have like six days of beam time, and because you want to look at different compositions and temperatures, this means typically an inelastic scattering run will take about 3 to 6 hours, something like that. So once you started, you have time to go and get something to eat and come back. This means pretty much, and the poor instrument scientist will probably have to change a sample in the middle of the night or something. But anyway, they get used to that.
Bien, si no hay más preguntas, entonces de nuevo muchas gracias a todos ustedes por estar aquí. Esperamos que toda la experiencia haya sido una experiencia muy enriquecedora. También esperamos que si ya han establecido contactos para oportunidades de cooperación, de todos modos las ofertas siguen en pie, los profesores podrán atender solicitudes de los profesores y los estudiantes después. Y entonces, de nuevo, muchas gracias a Marilena por toda la organización, al grupo de películas delgadas y de nanoestructuras, al Centro de Excelencia de Nuevos Materiales, también por toda la colaboración en el proceso, a toda la gente que ha hecho posible, digamos, hacer esto en una forma técnicamente adecuada. Las transmisiones se hicieron video streaming, pues en esencia para que cualquier persona con un computador pueda verla desde cualquier parte del mundo, y las conferencias han quedado grabadas en YouTube, así que están disponibles en YouTube desde una vez. Luego trataremos de editarlas para que quede el logo de la Universidad del Valle, supongo. Y finalmente, muchas gracias entonces a Marie-Louise y a David por su amabilidad, por tomarse 2 semanas de su tiempo para venir a Colombia y estar con todos ustedes. Muchas gracias a ellos.
Ellos quieren una foto con los profesores. Entonces, yo creo que lo mejor es que nos pasemos acá con ellos para que quedemos más cerca, porque aquí quedamos muy dispersos. ¿Ah? No.
Sí, sí, sí. No, me llamaron para hacer la traducción.
Yo me quedo por si algo.